Today, I'd like to talk a bit about my current research and specifically focus on the idea of human decision-making and what happens when we use suboptimal strategies and what this really means in terms of bias-variance trade-offs. So before we get there, what I'd like to do is just start by thinking a little bit about decision-making as a whole. And so specifically, I want to start by thinking about how context really dictates how we make our decisions. So for example, let's imagine that we're a zebra and we're interested in finding food. And so if this is a foraging problem, we can think about our decision in terms of where do I want to go? How many other zebras are foraging in the same area? Are there predators in this area? There's all of these components that we have to consider, and those components are going to be different based on the context. So in comparison to a zebra, we can do something like considering the weather. What clothes am I going to wear? Now, it doesn't matter how many other people are around me. What matters is, do I think it's going to rain? Is it going to be cold? And so there are these features, and we're going to weigh them with different importance in our decision based on that context. So one last example, we can say, let's say this is American football, but let's say that our quarterback here wants to pass the ball. He has to consider who's open, what are the opportunities, how soon do I need to make a decision, and are things constantly changing? I have to adapt for that. So the real point of this is that a decision is not just one particular strategy, but instead has to be considered with all of the features of the environment. And so once we consider those features of the environment, the other component for our decision that's going to be important for today's talk is that we're going to go through and think about, well, what are the elements of the decision? So in this case, I like to think about the elements of a decision as three pieces. The first component that we're going to consider today is going to be the expectation. And when I say expectation, we can think about this as our prior belief going in. So what do we believe to be the best choice before we even consider the evidence at hand? And just so that we're all on the same page, our expectation does not necessarily have to be the same as reality. So everyone can have different expectations. And then the second piece that we're going to combine this with is the evidence itself. And so when we talk about evidence, there can be many different features of an environment or a context that are going to actually impact our choice, right? And when we're talking about the evidence, we're going to accumulate this information that educates our decision. And so the third element of this decision is really the decision rule. And when we say decision rule, it's a question of how are we combining our expectations with the evidence at hand. And so this combination is the rule that we're going to use. And so from that decision rule, we end up with a choice. So all of this is really to say, great, we have these pieces of a decision, we want to consider these elements, but what does that mean for today's talk? So today, what I want to focus on is really the idea of asymmetric evidence. So we're going to spend most of the talk focused on this component. And the way that I find easiest to explain the idea of asymmetric evidence is with an example. So when we think about asymmetric evidence, let's take a little thought game here and say that we're a physician. And our goal is to diagnose a patient with epilepsy. So as you see, can't get too far from my epilepsy background here. So if I have a doctor who's trying to diagnose a patient with epilepsy, we can go through those three elements of a decision. So again, our expectation in this case is going to be, well, what is the percent of the population with epilepsy, right? How likely is it that this is a diagnosis to begin with? Then we have, for our evidence, in this case, we're going to use the example of a symptoms log. Have a patient actually track, well, did they have a seizure or was there any sort of clinical episode on any given day? And then we have our decision rule is going to be whatever that diagnostic rule is, and we're going to come back to that in just a second. But before we do that, let's just take a little bit of a stronger look at this evidence itself. So if we have a symptoms log, let's say that we look at 1 week of what our patient has reported. If we were to stop at this point, we'd see that there's no seizures at all. And we would conclude, probably logically, that there is obviously no epilepsy in this patient. But if we extend this, we see that we now have reported 1 seizure. And what this means, and the reason that we want to consider sort of the amount of evidence we're accumulating, is if something is rare or a piece of evidence does not occur often, then it may need to be weighted asymmetrically. And so in this case, if we go to that diagnostic rule, we can say that this asymmetric weight comes from the fact that 1 seizure is going to be more important to my diagnosis than all of the days without a seizure. So we actually have different weights. And so now we're going to say, okay, well, if 1 seizure is more important than 13 non-seizure days, my patient has epilepsy. So I've made a choice. So this kind of variations in weighting is really what we're going to focus on today. So now that we have sort of an idea as to what asymmetric evidence is in this context, I'd like to describe a bit of a more generalized task that allows us to describe the ideal observer for this case. So the task that we've developed is a basic jars task. And in this task, there's a set of 2 jars, one which is going to be called high, which is going to have more red balls, and one which is going to be called low, which has fewer red balls. And a sample of balls are drawn with replacement. And the goal of our observer is going to be to report which jar they think these drawn balls come from. Now, the way that we can vary the weight of the evidence is by varying the ratio of red balls in each jar. So in the symmetric evidence case, we're going to have that the number of red balls in each jar are reciprocal. So there's the same number of red balls in the high jar as there are blue balls in the low jar. And so what this means is that for every ball drawn, it gives me as much information, or sorry, our observer, as much information about if it's the high jar or the low jar. And we'll come back to that in a moment. In contrast, in the asymmetric evidence case, we now have the red balls that are rare in each jar. So they make up less than half of the balls in the jar. And kind of based on that same idea as the seizure, what we're now saying is these red balls should be weighed more heavily in our decision. So let's now take those components and build an ideal Bayesian observer. So in this case, we're now going to be able to define our expectation as the prior. And in this case, we're going to say that the prior of each jar, so the probability of each jar is going to be equal. Each jar is equally likely on every trial, so we're going to say that it's equal to 0.5. Now, we have to again consider the evidence. And so evidence in this case is a ball draw. And so we can describe this by now saying, well, what is the probability that a particular color ball is drawn from the high jar or from the low jar? And we're going to compare these two. Now, because our observer actually knows what these ratios are, so here H plus and H minus actually tell us the relative number of red balls, we can describe this explicitly. So now the third component is again that decision rule. So in this case, our decision rule is going to be based on a log likelihood ratio. And so what this is now combining is that iteratively for every ball drawn, we're going to combine our evidence with the past beliefs. And so in order to incorporate that expectation, we're going to start at Z0 is 0. So if we just look at what this means mechanistically and go through what all these components actually are doing, let's take, for example, what happens with these sample of balls drawn here. So now our belief, or our observer's belief here, is going to be based on each of those ball draws. And so what we can see is that for a blue ball drawn, it's going to be in favor of H minus, right? It's going to be evidence in favor of a lower jar. And so as we update with each ball draw, we shift. But what we see now is when we hit this red ball, the shift that occurs in our belief is larger if we see it in an asymmetric case than in a symmetric case. And so what happens after we combine all of our sample ball draws is that if our belief is positive, the observer reports that this is the high jar. If it is negative, it reports that this is the low jar. Now, this is how we go through what happens on a single trial. But what we're more interested in is how do these asymmetric evidence weights impact choices across many trials? So what we can do now is think about this more of a distribution of what happens, let's say, when we draw 10 balls. So when I draw 10 balls, we now have the option of looking at how likely the certain number of rare balls, and rare in this case is going to be red. So rare, red, I'm going to use these synonymously. And so we see that in the symmetric case, it makes this nice even distribution. So in this case, we can compare this to the log likelihood ratio of our observer. And so at 5 red balls, it's 0. So our observer is going to guess. If it is fewer than 5 red balls, the log likelihood ratio is going to be negative. So it's in favor of this low jar. That's why they're dark. And if it is more than 5 red balls, it is positive. So we're in favor of the high jar. So we see this nice even breakdown. However, when we instead consider what happens with the asymmetric jars, and again, we're looking at 10 balls drawn, we now see that because we have these red balls that are so rare, we're going to have many fewer trials that are going to have, let's say, 5 or 6 balls drawn, red balls drawn. So instead, we now have this skewing towards a much lower value for the rare balls drawn. And so we can see this reflected in the LLR. Now we again have 0 has shifted down, and this negative component is much shorter. But what we have to keep in mind is that actually this component that is in favor of the low jar is now making up more than 50% of this distribution. And so this is really interesting. And if we plot this a different way, it'll make it even stronger. What we're in essence saying is that over many, many trials, the response fraction of the ideal observer is going to show a choice asymmetry when we have asymmetric evidence. And what that means is that we're going to have the ideal observer responding in favor of the low jar more often than the prior would suggest. So the prior would assume that over many trials, each jar is responded for 50, half and half. But here we see that there's actually a choice asymmetry where it is enhanced. So this is what happens with an ideal observer. And so this leads us to a really interesting question, which is, well, does this choice asymmetry, how is that really modulated? And let's say that we're not using an ideal weight. How does that change these choice asymmetries? So let's just break it down and think about those weights again. So in this case, we're going to go back to those sample of balls drawn. And we're going to consider the symmetric case first. So we have our symmetric jars, and let's just walk through what happens if we have ball weights where the red ball or rare ball is underweighted. So it weighs less than the blue ball. In this case, we see our blue balls are going to win. We have a low jar response, and our response fraction is again going to deviate from the prior. But this isn't ideal for the symmetric evidence. So with the ideal, we get exactly what we saw in the last slide. Each ball is weighed equally to one another. We get this nice symmetry of our responses. And again, if we overweight, we're going to see a shift now in favor of the high jar. So we can modulate this just by changing the weights. Now, importantly, when we look at the asymmetric evidence case for the same concept, now, if we were to use the symmetric weights, we're actually going to get an enhancement or an exacerbation of that choice asymmetry. So remember that symmetric weights are not useful when an asymmetric evidence case. So here, the ideal is going to always be to have the red ball weigh more than the blue ball, which gives us that choice asymmetry from the last slide. And again, if we overweight that, we can actually shift back towards our prior. Now, the reason that I wanted to focus on these changes, if we were to use a mistuned weight or a suboptimal weight, is because it lets us identify two possible features that are going to be relevant for human inference later. The first one is what we can call accentuation. So if our ball is underweighted, we can accentuate this choice asymmetry and get a bias. On the other hand, if we are overweighting that red ball, we can view it as compensation, trying to match that prior, right? And so this sets up an interesting question, which is, what do humans do? Are they capable of, are they uncomfortable with this choice asymmetry and try to compensate to match the prior, which is known to be 50-50, or is it accentuated in some way? And so we have now some suboptimalities that we can understand and interpret. But we need some tools in which to actually do this interpretation. So in order to interpret this, what we're going to do is consider a psychrometric curve. So in this case, the psychrometric curve that we're going to use is going to compare the log likelihood ratio, which in this case is again based off of our ideal observer. So it's saying I've summed up all of these balls I've observed based on the ideal weights. This is the log likelihood ratio, and compare that to how often an observer responds in favor of the high jar. And so what this means for an ideal observer is that they're going to always respond in favor of the low jar when negative. So respond in the high jar 0% of the time. At 0, it's going to guess because the LLR is uninformative. And then when it is positive, we're again going to always respond in favor of the high jar. So this is what an ideal observer's psychrometric function would look like. But more realistic to human and suboptimal models is something that looks a little more like this. And so what this is saying is that we can have data points that are sampled at various LLRs, and we're going to fit using logistic regression. And the reason that we're going to do this and build these psychrometric functions is that there's a few key features that we can actually use and extract based off of this fitting. So for example, there's two key elements that we're going to consider today. There is a shift to the right or to the left, which we're going to consider a bias. So this bias is going to actually represent a change in maybe that overweighting or underweighting. But the other element and component that can be changed in the psychrometric function is really this slope. And this deviation of the slope of our sigmoid here can be broken into two pieces. And so both are considered parts of variability. But I'm going to break this down one step further. And we're going to say that the amount of deviation in the slope, so as it flattens, is going to be defined as noise. But more importantly to today's talk, the actual distance or error between where our data points are and the fit logistic regression or the fit logistic function is going to be called variance. And so the reason we want to describe this as variance is that these deviations may not represent just noise, but actually systematic differences in strategy. Remember that when we're looking at this particular psychrometric function, we're comparing it to a log likelihood ratio. And so it assumes that they're using a Bayesian update. We're adding up all of the evidence available, but that is not necessarily true. And so this gives us the ability to actually consider a few of these different components that may be driving some of the differences we'll see later. So just to put this in a little more context now, we are going to go back to what we saw with that asymmetric evidence. So remember, we saw that our ideal observer was showing this choice asymmetry, responding low more than 0.5. And so if we look at what happens, we can now see that a bias where we're shifted to the left is going to be relevant to that compensation that I mentioned before. And so what this is going to respond to is, again, we're now lowering the amount of responses in favor of the low. If we instead have a bias to the right, this is going to be correspondent to accentuation or underweighting. And now this is sort of counterintuitive. When we have these variability metrics, they do not necessarily reflect a deviation in our choice asymmetry. And so this is why we need to both combine our understanding of how we're approaching asymmetric evidence with something like these psychometric functions and these bias and variance metrics. So keeping all of this in mind, we now are able to actually ask the question, which is, well, what do humans do when presented with asymmetric evidence? And so the way that we went about this was to use online crowdsourcing, and we used that same jars task. And we asked subjects, please report which jar you think you are using. And we gave them 5 different blocks. So there was a control, a very simple, easy task to begin with. And then we varied both the difficulty and the symmetry. And so we have both a hard asymmetric, a hard symmetric, easy asymmetric, and an easy symmetric. And what we see is, regardless of the difficulty of the task, both our subjects and of course our ideal observers show this choice asymmetry. And so in this case, the ideal observers that I'm showing you are actually sample matched. So they're doing the exact same trials as the subjects were doing. And so we see that we have both the subjects and the ideal observers that are showing this choice asymmetry. But how do they really compare? So even if just by eye, we can see that in this case, a majority of our subjects seem to be showing more choice asymmetry than the ideal observer. So let's just go back a moment and figure out this plot. So we're going to now compare for each subject, what is the bias and the variance term from those psychometric fits. And so if we start with the symmetric evidence case, what we see is that across the population, subjects are showing psychometric fits that look extremely similar to what an ideal observer would predict. The only deviation here is in the direction of variance. So really, there isn't a whole lot of bias going on in the symmetric case, which is exactly what we would expect. However, when we instead consider the asymmetric evidence, we see that not only is our psychometric curve showing this much smoother sigmoidal function, so it has quite a bit of variance in it, it is also showing a shift, specifically in favor of the low jar. So they're showing increased choice asymmetry. So now this asks the question, well, what is causing this? Is it true that these subjects are misweighing their evidence using Bayesian models, or is there something else happening here? And so the next thing that we sought to do was to actually ask, what decision rules do humans use? So the way that we're going to go about this now is that we came up with a set of models, and they came in 2 flavors. So the first and the base model we're going to use to define this is what I'm going to call our noisy Bayesian model. In this model, again, our subjects are going to add up all of the balls that they see, but we are now considering that the rare ball weight is now going to be defined as rho. It is a free parameter. So this will allow us to actually fit and see what is most likely. Is there an underweighting, an overweighting? Is it similar to the ideal observer? And so then we included some noise and we get our belief. Now, there is the possibility though that we have subjects that are using the same rare ball weight as the ideal observer, but just with some noise. And so I'm going to call this the set rho. And so here, I'm just going to set it instead to the ideal observer, which reduces this model complexity, so there's only a noise component. Then the next version of this is, well, a prior model, right? Maybe their expectation going in is biased. And so we're going to consider a model in which the ideal observer weight is used, but there's a biased prior going in. So these are our Bayesian models, and you'll notice I put them in purple because these are related to the LLR and should correspond with more of these shifts rather than deviations in the slope. On the other hand, though, we have these heuristic models that we can also consider. And so the main one that we're going to think about is what I'm going to call a rare ball model. So in this case, we're going to think about a rare ball model as a very simple heuristic in which if a rare ball or a number of rare balls is seen, then with some probability, the observer responds high, and with some probability, they respond low. So in this case, when we have a variable rare ball model, the number of rare balls needed to be observed in order to respond high is a free parameter. So, right, a subject may like to see 2 balls before they respond high, or 3 balls. Now, a simpler version of this is what we call a rare ball model. And in this case, we're going to just set that threshold to 1. Any red balls is going to correspond with a high response. And so when I say that there are these probabilities, in the most extreme case, what this is saying is I see a red ball, automatically respond high. So then in order to just encompass, maybe they're not using any strategy whatsoever that includes evidence, we're also just going to have a guessing model. And so with some probability on every trial, our subjects are going to select an answer. So in order to identify which model is actually the most relevant to each subject's responses, we're going to compare using Bayes factors. And so in this case, when we talk about Bayes factors, I'm considering what is the probability that these responses came from a particular model as compared to the probability that these responses came from this noisy Bayesian model. And so by doing this, this allows me to actually differentiate whether or not we think an alternative model is better than this noisy Bayesian base model. And using this sort of comparison, what we find is 2 really interesting features. So the first is that across the board in almost all of these subjects, so majority of subjects are using Bayesian-based approaches. But what's really important is that Bayesian does not necessarily mean ideal, right? It is not necessarily optimal. And in this asymmetric cases, especially the difficult ones, so this is the hard asymmetric block here, there's really a lot of variability in the types of strategies that are being applied. And so this now allows us to go back to the same question from before and say, okay, well, we saw that we had this skewing with bias, and there was quite a bit of variance. Where do each of these subjects fit? So here, we're going to return to that plot we had before, where we had bias and variance for each of our subjects. But now what I've done is for each individual, I've color-coded them based on the model that best described their responses. And now we can really break this down into 3 groups. There's a group of subjects that are focused on nearly ideal. So these were subjects that best matched the set row. So they're using the ideal observer's weight with some amount of noise. And then we have a group that we're going to call the suboptimal Bayesian. And in this case, this is a noisy Bayesian model or a prior Bayesian model where they're not quite doing this accurately. And then the third group is our heuristics, anyone using a rare ball or a guessing model. Now, what happens if we look at the medians here is that we see that there's a very distinct shift where our suboptimal Bayesians are the ones that are describing most of those subjects out here with bias, whereas our heuristics are actually the ones showing more variance. And if we go back to sort of that prediction from before, we now see that our suboptimal Bayesian models are the ones that are showing that enhanced low jar response, whereas our heuristics are showing pretty equivalent low jar responses. So that choice asymmetry, that's pretty equivalent to our ideal subjects. So now that we've really differentiated that there's three groups, can we actually say something about why these suboptimal Bayesians are showing this bias? Is it truly, as we predicted, this underweighting? And so again, we'd said that the suboptimal Bayesians were from two best fit models. So first, let's look at that noisy Bayesian model. And if you recall, we said that there is a free parameter rho, which defines the rare ball weight. And what we see is exactly in line with as we predicted before. These subjects are underweighting their rare balls. So here I've now plotted what the ideal observer defines as the appropriate rare ball weight in this particular case. And these are our subjects' best fit rare ball weights. And we see that they are definitely trending closer towards what would happen in a symmetric case. So this definitely describes half of it, but we also had quite a few subjects that really were coming in with just a bias expectation. And so they showed a low jar preference from the get-go. And so there's more than one way that you can get these biases, but these biases are really distinct to these more Bayesian-based approaches. So keeping this in mind, we now have the ability to say, great, we're seeing some differences in bias and variance between these different subgroups. But what does that really mean? We've talked sort of generally about the idea of bias and variance, but if you've noticed, I haven't mentioned sort of the more common bias-variance trade-off as of now. So I just want to take a moment to discuss when we typically consider a bias-variance trade-off, it's in terms of model fitting, and we think about it as bias being enhanced when we are underfitting and variance being enhanced when we are overfitting, and trying to find that optimal balance. But this particular description of bias-variance trade-offs assumes that for a given model complexity, you are using the optimal version for that complexity, right? You're using the best model at that complexity, which may or may not actually be the case. And so in order to see how our models compared, and if we could really interpret this in some sort of a bias variance methods, we're gonna actually go and now say, great, let's actually come up with a metric for complexity for this particular situation. So the metric that I'm going to use today is going to be mutual information. And now I would just want to walk us through this very briefly. When we're talking about this metric for complexity, you'll notice that I'm now reducing this, it's model free. So we're only going to consider elements that are relevant to the evidence. So here, we're going to describe mutual information in terms of the number of rare balls that were seen in a particular sample, the number of observations total, and the choice, right? What is the response? What jar did you choose? And so I just want to make it very clear up front, when we define complexity in this case, we are assuming that this is only mutual information for relevant evidence to the trial. So this is not to say that a model can't have complexity by tuning to other irrelevant features. But we're going to stick with this component today and just see for what should be considered, how do each of these models do? So using this form of mutual information, what we're able to do is first start by comparing now what happens if we think about a given level of mutual information in this case, and the accuracy that we would expect in this task. And what this allows us to do is now create a bound. So this bound here is saying for the ideal observer, if they were to use a particular level of mutual information, so complexity, how well would we expect them to do? So using this bound as a metric, we can now see where our subjects lie in comparison. And so in this case, again, I have color-coded each subject based off of the model that best described their responses. And I've again broken them into those three groups. And so now there's really two interesting components that come out of this. The first is that we see our nearly ideal subjects are using the most of the relevant information. So they are the most complex using this mutual information metric, followed by these Bayesian models, and lastly, these really simple heuristics. So this is very good sanity check. It goes with the intuition we would expect. But the other thing that is really critical to notice here is that how far each of these subjects is from the bound, this optimality bound, changes as well. So we have this shift, meaning that a lot of these subjects are not only using not necessarily as much information as available, so not as complex as it could be, but they're not using it optimally even in that case. So we're really dealing with these suboptimal subjects. So keeping this in mind, we now are able to actually approach the question and ask, okay, how does this relate now to bias and variance? We know we're not using optimal models necessarily. So are these trends sustained? Is it true that there's more bias or variance in either case? And so what actually happens when we deal with these suboptimal versions of these models is that we're seeing that the bias-variance trade-off inverts. And so the way that we can look at this is if we now compare, again, our mutual information to those bias measures that we had from before, we see that our more complex but suboptimal Bayesian models are showing more bias than our heuristics, whereas with our variance metric, our heuristics are the ones showing more variance but lower complexity. And so this is the exact opposite of what we typically consider in terms of bias-variance trade-offs. Now, one thing that could occur at this particular point is we say, okay, well, how do we know that this isn't just the effects of human idiosyncrasies, right? Maybe this is just particular to our subject group. So in order to mitigate this, what we did was to take this one step further and say, okay, let's put this to the side and let's instead create synthetic responses generated from the models that we've now identified as being relevant. And so what I mean by that is that we take each of the models that were identified for our human subjects and the parameters that were fit to those subjects, and we generate new data sets with new sets of actual observations and trials. And let's walk through this again. And so we see again, here's our bias versus our variance for these same synthetic subjects now. And we see that we have the exact same trends as before. Again, our suboptimal Bayesian models are showing this bias in favor of accentuation, and our heuristic models are showing more variance. And if we go through this again, we can see, as confirmed with before, our mutual information shows that only our suboptimal models are showing this increase in bias, but more complex. And our heuristic models are showing this increase in variance, but less complex. So this cannot just be based on the subjects themselves, but there seems to be a more relevant feature here. And so with that, I just want to spend a moment recapping what we've discovered today. So first thing that we discussed is that when we consider asymmetric evidence, both an ideal observer and human subjects show a choice asymmetry. And what's really fascinating about this is that many of the features that we discovered within the human behavior would not be noticeable when we use symmetric evidence, which is very common in most of the decision-making tasks that we typically deal with. So this in itself is really interesting, that we can have an ideal observer that deviates from the prior and that these subjects are matching that. However, while they're matching that, subjects are not necessarily doing this optimally. While most apply a Bayesian approach, Bayesian models are very difficult to fit. It takes a lot of energy. And so it's not necessarily surprising that these are mistuned Bayesian approaches. And that's leading to some sort of deviations from what we would expect from the ideal observer. And lastly, that these suboptimalities actually follow a really interesting trend, which is that as we look at complexity, a more complex but suboptimal model is going to enhance bias, whereas a less complex suboptimal model is going to enhance variance. So this goes against what we typically consider. And so with that, I would just like to acknowledge my mentors. So Zach Kilpatrick at the University of Colorado Boulder, Kresho Yoshik at the University of Houston, and Josh Gold at the University of Pennsylvania.